Digital Logic Design lecture. In this lecture, I will talk about combination logic with MSI and LSI. The term MSI and LSI means medium scale integration and large scale integration. So far in our previous lectures, we had used classical method for simplification using Carnot map. So we actually used to design or use a small scale integrated circuits, which included around 1 to 12 or 13 logic components or logic gates. In MSI, normally MSI circuit, medium scale integrated circuits, normally include 13 to 99 logic components. And similarly, LSI, large scale integration, involves 100 to around 10,000 logic components. And then there is a term VLSI, which means very large scale integration, which include 10,000 to 100,000 logic components. So the number of logic gates or the logic components increases. In this lecture, there are subtopics. The first one is 4-bit binary parallel adder. So I will design a 4-bit binary parallel adder in this lecture, and then there is a problem which is called look ahead carry generation or propagation delay. So we will be using a look ahead carry generator to avoid that propagation delay. And then I will use this look ahead carry generator to design a binary adder using carry generator. So this binary adder would be without carry propagation delay, which would be much efficient than the first 4-bit binary parallel adder without carry generator. So let's begin with the first one. This is a full adder. We had already talked about it. This full adder has been implemented using exclusive OR gate. We had already shown how to implement a full adder from typical AND and OR gate to exclusive OR gates. This implementation is quite compact and quite useful to analyze or to investigate carry propagation in n-bit binary parallel adder. In this full adder, we already know X and Y are the 2 bits that this full adder adds, along with an input carry, which is Z, and it produces a sum bit and a carry bit. I will use this full adder, this description of the full adder in further investigation. Let me give you an example. If you want to add 2 4-bit binary numbers, and I want to design a 4-bit binary parallel adder for adding 2 4-bit numbers. Let me take an example. The first 4-bit number is 1011, and let me call this number A. The subscript I is used to identify a bit at a specific significant position. So the subscript I actually represent the significant position, and it begin with 1, 2, 3, and 4. So these are actually the bit position to identify each bit. So A1 would mean this bit, A2 would mean this one, and A3 would mean 0, A4 would mean this one. So this is number A, 4-bit number A, and let me take another number. And just to relate this with the previous full adder that we had talked about in previous chapters, these bits would be represented with X in the full adder, and it's also called Ogen. And another number is B. Again, this is a 4-bit number, and in this particular example, this 4-bit number is 0011. So quite similar to A. I, this BI is used for to identify the significant position of the bit. So B1 would be 1, B2 would be 1 and B3 is 0, B4 is 0, and this number is also called addend. In the previous full adder, these bits would be represented with Y in the full adder. So we want to add these two binary numbers, and obviously, as we have already talked about this, we would add 1 1 as we do in the typical decimal system. At this particular significant position, the bits would be added, and if there is a carry, that carry is moved to the next higher position, which is position 2, and is added here, and the sum is calculated, and the carry is added in the next 2 bits at next higher position, and so on and so forth. So let's do this. Here is the input carry. The input carry at each position is the carry taken from the previous position. So initially it is 0, and when we add these 2 bits, we create a sum bit which would be shown shortly, and the output carry is moved to the next higher position, and then it is added with the next 2 bits. So these are the 2 bits of the 2 numbers, and this is the input carry from the previous position, which is taken from here. So let me add the sum bit as well. So in this complete example, initially for the first 2 bits on the rightmost position, the input carry is 0. It is always 0, and these 2 bits are added. So when these 2 bits are added, 1 1 is 1 0. So 0 is the sum, and 1 is the carry to the next position. And this carry is also recorded here, which is the output carry, and this output carry is also considered as the input carry to the next higher position. So at the next higher position, as we have taken a carry from the previous position here, and at this position we have 2 bits, which is 1 1, and we have a carry which is 1 also. So when we add these 3 ones, we would get 1 1. So 1 is the sum, and the other one is a carry to the next position, and this is also recorded here, which is the output carry. So at this position we got 1 0. So 1 is the output carry, 0 is the sum bit, and this one is also represented as the input carry for the next higher position bits. Okay, so we added these 3 ones, and we got 1 1. So 1 is the sum, and 1 is the output carry, and this one is again moved to the next position as an input carry, and is added to the next 2 bits, which are 0 0. So 0 0, and this one becomes 0 1. So 0 is the output carry, and 1 is the sum, and this 0, which is the output carry, is also moved as the input carry to the next position. And at the next position we have the 2 bits 1 0, and this is the input carry. So the sum is again 0 1. So this 0 is the output carry, and this one is the sum. As we have no other higher bits to add, so we don't create an input carry for the other position. If there would be 2 other bits, then we would get at the 5th position, we would get this 0 as the input carry. So we stop here. So just to relate to the previous full adder, the bits of the number A are represented with X in that full adder, and the bits of the number B are represented with Y. The input carry is Z, the output sum is S, and the output carry is C. And this is also the subscript I is used for the corresponding bit position, as we used with the number A, B, and K input carry. And here CI plus 1 is used because this output carry is actually the input carry at the next higher stage. For example, at position 1, if we put I is equal to 1 here, then the output carry produced at position 1 is the input carry at position number 2, and it can be calculated as put I is equal to 1, so 1 plus 1 is equal to 2, so this becomes C2. So C2 is actually the input carry at next position. So when we calculate the output carry at particular position, at particular significant position, that output carry is the input carry at higher position, which is 2 in this example. So what we get at each position, we add 2 bit which are represented with x, y, or a1, b1, or in general ai, bi. We get an input carry which is represented with ci, and we get a sum bit which is represented with si, and we get an output carry which is represented with ci plus 1. So here we have all the possibilities. We have specific variables for just 2 bit x, y, z, s, and c, and we have generalized variables as well. Okay, so for each significant position, we can reuse this kind of full adder, and at each position, for example, if we use this full adder, a1 would be this bit, b1 would be this bit. If I is equal to, when I is equal to 1, then in this diagram, a1 would be this bit, b1 would be this bit, c1, which is the input carry, would be this 0, sum, which is s1, would be 0, ci plus 1, which would be c2 actually, so c2 would be 1, and this c2 is actually the input carry at position number 2, so that's why ci plus 1 is used. And similarly, if when I is equal to 2, then a1 would be 1 in this particular example, b1 would be 1, c1 would be 1, s1 would be 1, and c3 would also be 1, and so on and so forth for other bit position as well. Okay, so for each bit position, for the first bit position, c1, if we represent that full adder, this full adder as a block, then we would refer to the full adder at first position, full adder 1, fa1 for simplicity, and the first input carry would be c1, which was 0 in the previous example, and the first organ bit would be a1, the first add-in bit would be b1, the first sum bit is s1, and the output carry is c2. So this is the description of the full adder for the first pair of first significant position, at the rightmost significant position, and for the next higher position we would use another full adder, which we would call full adder 2, and the first organ bit would be a2, add-in bit would be b2, and the input carry to this full adder 2 is the output carry from the previous full adder, which is c2. So this c2 is actually the output carry of full adder a1, but it is given as an input to the full adder at next higher position. And for the significant position 3, we would add another full adder a3, fa3, and similarly a3, b3 would be the 2 bits. The input carry at this position would be the output carry from the previous position. The output carry of this full adder 2 is given as an input to the full adder 3, which adds actually the 2 bits at the third position. This full adder adds the 2 bits at the second position. This full adder adds the 2 bits at the first position. And for the fourth pair of 2 bits, we would add another full adder, which is referred to as full adder 4. It adds the 2 bits a4 and b4, and an input carry taken from the previous bit position C4 and produces a sum bit S4 and produces an output carry C5. So this is a 4-bit binary parallel adder. Each block is a full adder of this form: AI, BI or A1, B1 for the first position, CI is C1 which is initially 0, SI is S1 for the first position, CI plus 1 is C2, C2 for the first full adder, and similarly for the other full adders. So this full adder gets A1, A2, A3 and A4. This is the first number, 4 bit of the first number, B1, B2, B3, B4, 4 bits of the second number, an initial carry which is initially 0. It produces 4 bits of the sum S1, S2, S3, S4 and a final output carry C5. And of course there are 3 input and output carries as well, C2, C3 and C4, but these 3 carries are generated and given as input internally from one full adder to the other. As a block diagram, it would be represented like this: 4 inputs which represent a number A, 4 bits of number A, 4 inputs which represent number B, and an initial carry C1. So actually we have 9 inputs and 4 bits of the sum and an output carry. So these 5 are the outputs. So this is a 4-bit binary parallel adder. It's actually the block diagram of a 4-bit binary parallel adder. This is an IC package, and this full adder, binary parallel adder, has been implemented using 4 full adder circuits. Now I will give you an example to show the significance of this integrated circuit, and will show you how such kind of integrated circuit package can be useful to implement a function so easily. Now let's consider to implement BCD to XS3 converter. We have already designed BCD to XS3 converter, and we have using conventional method, using K-map method. Conventional classical K-map method is useful when we want to design a small scale integrated circuit which includes just few logic components, but that is not always useful. In K-map method we talked about to design an economical or cost efficient logic circuit by reducing the number of logic gates, but this is not always true. Actually there are a number of integrated circuits packages commercially implemented, and they are available in the market. Sometimes it is more economical to use as many as logic gates from an existing IC package than to implement it from the scratch using conventional classical method. It is not always the number of gates to reduce the number of gates, but it is sometimes the implementation of an existing IC package to implement a desired logic function. For example, when we want to implement a logic function, there would be a large number of internal connections. These internal connections are not good. If there is an existing IC package and if we implement that or include that IC package in our circuit, then obviously there will be reduced number of external connections and wires. These external connection and wires, reduction of external connection and wires result in efficient circuit. And also there are more number of inputs in a logic circuit than using K-map method. This is simply not feasible to implement using K-map method. For example, using BCD to XS3 converter, we have already seen that there are 9 inputs and 5 outputs in BCD to XS3 converter. Now using K-map method, we would have 2 raised to power 9 rows in the truth table, and we would require 9 variable map. So as imagine that even 6 variable map is too cumbersome to design and to simplify. Now imagine in this BCD to XS3 converter, if we use classical method, we would require 9 variable map and we would require 2 raised to power 9 rows in the truth table. So this is simply quite complicated. This is not possible this is possible, but this is quite tedious. So using combination logic with MSI and LSI approach, we are thinking about reusing an existing IC package. So we have already this IC package, a binary parallel adder, which is shown here as a block diagram. We have 4 inputs, a binary for the binary number A, and we have 4 inputs for the binary number B, and we have an input carry, and it sums the two numbers and produces 4 bit of the sum and an output carry. Now let me show you how to use this IC package to implement BCD to XS3 code converter. Now if we think a bit the functionality of the BCD to XS3 converter, how BCD to XS3 converter work, then we already know that in a BCD to XS3 converter, actually binary 0011 is added to the BCD input. An XS3 code can be achieved from the BCD code if 0011 is added to the BCD code. For example, the BCD code of 0 is 0000. When 0011 is added to that BCD input, then it becomes 3 in decimal, and in the binary it becomes 0011. So if we get an BCD input and we add 0011 to the BCD input, then the sum result is XS3 output. So we can use that block diagram of binary parallel adder, which is shown here. The first number, 4-bit number, is BCD input to this adder. So the BCD number is a 4-bit number, which is given as an input through these 4 input pins, and the second number is a constant, which is 0011. So what we do here, we make these two inputs as 0 and we make these two inputs as 1, so it becomes 3 in decimal, and in binary it becomes 0011. So each time when this circuit gets a BCD input, 4-bit BCD input, each time a 0011 is added with this input, and the sum is obviously XS3 output, because we can get an XS3 code up a digit if we add the 0011 to the BCD of that digit. And each time initially C1 is 0, and internally if there is a carry, then it does all the rest of job, and the output carry is not used. So This is a block diagram, an IC package, a 4-bit binary added, and we are reusing this IC package. This is an MSI circuit, and we are reusing this MSI IC package and implement BCD to XS3 code converter. If we would be using this, if we would be implementing this BCD to XS3 code converter using conventional K-map method, then we would be using 9 variable map, which is quite tedious. So this is the benefit of combinational logic with MSI using an IC package. So we are reusing actually the logic gates inside this MSI chip. So there are internal connections, they are good, but there are very few external connections. So using as many as logic gates from an existing IC package produces economical combinational logic circuit.